separate scenes.
Okay, thank you.
Scene.
I'll try not to shout at you all.
Just looks like there's a scene.
Okay, I had this waking nightmare. I recorded a video of myself doing these slides earlier, and it seemed to save itself into PowerPoint. I had this awful thought that as soon as I started presenting today, you were going to hear my recording and see my nervous little face here. So that we've passed the first hurdle. So I'm Simon. I work for Ditto. My background is about 10 years working for different database companies and for Confluent. If anyone's used Kafka, you'll be familiar with them. I've been at Ditto about 6 months, and this is kind of my first try speaking to an audience like you about Ditto. So you give me feedback afterwards, please. Right level, wrong level, not interesting things, I'd love to hear it. So that's the little plea from me to you. But I'm going to talk about local first development, a bit about CRDTs and offline sync using peer-to-peer on iOS. And I hope you enjoy it. I'm going to start off with a slide that will make probably most of you roll your eyes. But most apps are reliable on the cloud connection or some sort of back-end connection to work. And of course, things can go wrong with that might compromise your user experience. Cloud outage, I won't even bother to kind of speak about, it happens. But more frequently, kind of, lack of reception, or the phone's OS is reporting to you that you have a data connection, but actually you've got spotty internet and you can't make calls outbound to do RPCs, and you end up with an app with spinners and unpleasant user experiences. The other things that could go wrong, a device dies, it thinks it's committed, but it hasn't, and a user has the perception that they've lost committed data. There are, however, kind of other ways to build, and I'm sure many of you actually use them, without relying explicitly on kind of the internet or a network to go and commit data to some remote backend. And I'm taking this 7 ideals for local first software from this Ink and Switch kind of paper. It's sort of a manifesto for developing local first software. It's not a new idea, but I think time has come, and the technologies to kind of support doing that and make it easy for developers are here. And the key things, I will run through them one by one, is really about keeping a lightning fast experience for the user of the app. So everything is being read and written to locally. Queries in general are executing locally. And you also can move data, your work, from one device to another. But the network is optional and the internet is optional. I'll talk a bit more about what is meant by that. Allowing collaboration is super important. So you think about the collaborative kind of experiences of using things like Google Docs and other tools, where you can still make local changes, see them appear remotely. And this point about the long now is really about not having data stored in a format or with someone else who, another system that may or may not be about in perpetuity. I think this is probably less of a concern for most of us because we tend to trust, hyperscalers and Apple and others, that if we store data with them in their services, they will be here for a long period of time. But having ownership of a local copy of your data in a format that you can read in future is valuable, I think more as a philosophy perhaps than in total practicality. And then ensuring security, privacy by default, and retaining ownership of control by having the local copy of your data be essentially the master copy and not surrendering that out to a database in the cloud. I'll just, 1 second, let me get my water. Jump to the most familiar example with a bit of whimsy. I think everyone is probably familiar with the source of the, I almost don't want to say it, GIF. Let's not discuss which one it should be. But the principle here is everyone's worked with kind of Git as a paradigm. You make local changes, other people make local changes, they push them to a remote repository, and those changes can be merged. And it works beautifully, and it's a brilliant version control tool. It works extremely well with code because it's built for line-based text files. So that kind of collaborative experience of doing things locally, pushing them remotely, merging them automatically in many cases, we're familiar with. But if you want to extend that to other data types, more general data types than text on its own, or code, you then have to address some other kind of fundamental challenges. And you can think about, the title of this slide isn't great, but you can think about the difference between kind of in distributed systems, a thin client and a thick client, where a thin client is really doing very little in terms of storage of state and processing itself and offloading all of that via typically like a REST or other API to a remote system. Mobile apps and mobile phones in general give you a great platform to build a thick client. Most apps are arguably thick clients, and you get big advantages like you can use local data stores, of course. I mean, I've got kind of SQLite and core data here as an example. Alternatives to think about might be more like PWAs, progressive web apps, where you have less ability to have kind of storage that can persist beyond the session of the application itself. Thick apps generally feel a lot faster and they give you the power to work offline. And the concept that's sort of worth introducing at this point is the back-end synchronization can be optional and it can happen in the background where you're working really principally on your local piece of data. And this is fine if you kind of set apart the collaboration requirement from those previous kind of 7 principles. When you start to introduce an application which could be of any class, but where you're modifying the same data records locally with a local data store, and other people could be modifying that as well, you're then introducing the classic distributed system problems. And generally, who wants to write their own replication, diffing, merging, conflict resolution algorithms? So thick clients like get you some of the way towards that local first pattern with local data stores, but they don't necessarily get you all the way with the handling of conflicts and concurrency and collaborative use cases. And most people will like turn to specialized backends for this. I don't have any particular attachment to any of these things, but you know, Realm, Firebase, CloudKit, CouchDB, others are out there, well supported and familiar, and let you treat on-device data, you know, in some respects as the primary copy with the backend sync. So they get you a good part of the way with a nice developer experience to the local first kind of paradigm and requirement. What they sometimes lack though is more the built-in conflict resolution capabilities that you need to build truly collaborative offline experiences. I hope this is clear. Okay, it looks large enough. Again, taken from the same paper on this as the kind of North Stars for how to build local first software and what we would be aiming towards. So fast, multi-device, offline capable software where you have collaboration built in, longevity of data, and you have privacy and control. And a big part of building towards at least the collaboration part, I think the sort of existing backends as a service get you the first 3 to an extent. The collaborative piece is extremely hard to build yourself. And that's where CRDTs come in. So who's familiar with CRDTs as a data type? Okay. A few hands went up. No shame in saying yes or no. So these are conflict-free replicated data types. The acronym's perhaps not perfect for that. And there are a number of libraries you can look up that will let you build with CRDTs. And what these do are give you automated building blocks to handle concurrent writes to the same data structures. So a simple example here, and this may be a bit small for people at the back, apologies, is really about ensuring in systems with optimistic replication. So you can think about any of these. I do something locally, I replicate it asynchronously, and I'm going to deliver it to someone else asynchronously as optimistic replications. You want to end up with every device, when that system is quiescent, i.e. all the replication has finished, everyone with looking at the same piece of data converges to the same eventually consistent state. And CRDTs basically data structures that build in automated methods to resolve conflicts, to merge data together without you having to think about that at development time. So the example here is something called a replicated growable array. I think the name is quite descriptive. If you have two peers, two entities, devices, they start at the same state in this to-do list, which just has an entry in it, which is watering plants, which is false. Device 2 wants to change the state of that to say true, they have watered the plants. Device 1 wants to add another entry, which is buy milk. They both do that on their offline data stores, replicate that data to each other. The CRDT can automatically merge that data together in a similar way to Git merging changes, in this case in an array where they converge on the same state, even though the writes were to the same array itself by remote parties. CRDTs are kind of the building block for building these applications. What I'm going to talk about, and it's specific to Ditto, but if you were to build it yourself, here's the recipe for allowing the power of CRDTs and local first without having to think about it all yourself. So one thing we can do is to build a familiar API around operating with CRDTs. And to do that, basically you build a CRDT database. So provide yourself with a document database, so you can make your local rights queries, you get all the CRUD semantics that you would expect, put this into your application as an SDK, and allow for it to automatically merge concurrent changes. If my local data store receives a change that was made on yours, it can merge those changes automatically. Gives you a way to build your apps around changes that are made either locally or by a remote party. So you basically have a live query saying, hey, I want to know about any changes that were made to data in this database, and get a callback anytime something happens, be it local or remote, so you can update the UI, and automatically resolve any conflicts with last write wins. In the case of Ditto, and part of the local first kind of manifesto is about making the network or internet optional. This database can also do peer-to-peer replication. And that means that you don't even need the internet to exchange data. And I'll talk a bit more about the scenarios where that can be useful. I just want to talk a bit about making the replication part easy. Because if we put our CRDTs into a database-like API, we can use familiar database paradigms like a query to decide which data to replicate and which we want to receive. So to make it as simple as possible, we can simply operate on our database, and the store is a collection of data. Say, I want to receive and distribute any data where this predicate is matched. It's an arbitrary predicate, in this case, red cars with a mileage of less than 5,000. Hit subscribe, and have the database itself handle all the replication for us over whatever transport we choose to use, and that could be internet or peer-to-peer transports. And later on we may want to kind of stop distributing or subscribing to data. But it gives you a very simple way to decide what data you're sharing. A lot of other kind of backends of the service will require you to replicate a lot more data, like an entire collection, rather than just the data you want. And if you start to extend to the kind of internet optional, offline, peer-to-peer scenarios, you don't necessarily want to ship tons of data because you don't have a ton of bandwidth necessarily. So allowing yourself to only sync what's needed, minimize data you're moving on the wire, and to only sync diffs is a core part of building a database around CRDTs. And I'll just briefly run through the kind of concurrency model and then come to wrap up in the next few minutes. In extending the scenario we looked at before, where you have changes made by different parties on the same kind of entity, what this is showing you is two objects. This is slightly different to the array example we saw before, two JSON objects where we're changing different properties by different users at the same time on their local store. Because CRDTs are used to automatically resolve and merge changes. In this scenario, there's no conflict, so properties can be replicated individually, and there was no conflict made between the same property being changed by the same entity on either side, so these can just be merged, and all of the subscribed peers to this data will converge on the same state in time. That's the kind of simple case. In the more gnarly example that actually we see in practice doesn't happen that often, if you do have writers on different local data stores writing data to the same property at the same time, the simplest model that you can build alternative models with CRDTs, the simplest model that humans can reason about is last right wins. I mean, it comes up all over the place. But in general, if you're dealing with human-generated data at the speed that humans can generate information, the ability for the database itself to resolve a conflict by simply saying, hey, the last writer on wall clock time and number of modifications will win, and the database will converge on that state. It means you don't have to plug in your own conflict resolvers, which can get very, very complicated. This is achieved in CRDTs usually using kind of hybrid logical clocks. So every writer of a CRDT is keeping track of how many changes it and others have made and the times that they were made. Just going to talk briefly about how we make the network optional. I think I need to speed up in fairness to others. If you've got an iOS device, you have incredible connectivity options available to you in that stack. So Apple multi-peer connectivity, I think previously was Apple Wireless Device Link. Devices can build peer-to-peer connections, and you can use that to build a peer-to-peer mesh, and indeed that's what happens within Ditto itself. Cool thing about Apple devices is you also have Bluetooth, and you can have simultaneous peer-to-peer Wi-Fi connections as well as infrastructure wireless area network connections. So you can have a mesh of devices hooked together. If I was on my own laptop, I'd show you a live example via Bluetooth, via peer-to-peer Wi-Fi over the LAN, doing discovery with MDNS over LAN and discovering local devices. So you can build very complex topologies with the power of that device without requiring any internet. Just so you are aware of what's possible with the chips in these devices, peer-to-peer Wi-Fi will get you about 80 meters and gigabit speed if you're within about 5 meters, drops off quite fast, but this is what powers AirDrop that probably everyone in this room is familiar with. The radios are actually really, really great and build extremely reliable connections. You've also got Bluetooth low energy, which you could exchange data. If you have a use case where you had local peers that were further apart, or you have more interference, as is likely to be the case in a building like this, you can get further with lower data rates. You're talking sort of kilobits with Bluetooth low energy, but it is exactly what it says. It's a low energy protocol, and it will get you a very far distance. Putting that together, you can build multi-hop meshes. So within our SDK, the SDK will find all local peers on any of the protocols discussed and build a mesh across all of those protocols and let you share data just with that subscribe method that I talked about earlier. So this will be a true mesh, like multi-protocol, and will constantly update itself and heal if things drop out of the mesh. So if you have scenarios where you want to share data very, very quickly, robustly, between multiple collaborating devices in a kind of geographically local environment, you can use this to do that in a robust way. I wanted to just dive very briefly into the detail on how this is actually built in our implementation. Our implementation uses kind of Rust at the core for the storage engine and the query engine, and then FFI bindings for higher level languages, Swift kind of primary amongst them, and then a transport layer abstraction that lets us use the relevant technologies on any platform. So this is iOS specific, so we've spoken really about the first two, or the first three on here, but it's also possible to build a system of iOS devices as well as Raspberry Pis, industrial machinery, anything that can run one of the SDKs that were at the top of the previous list, and have them all communicate across a heterogeneous mesh. So in this example, iPhones would communicate over peer-to-peer or WAN, or infrastructure Wi-Fi, and then also communicate with other devices over BTLE. Last couple of points to make. What sort of scenarios is this good for? We've seen a lot of adoption of the technology in the airline industry, sort of obvious reasons. You have unreliable Wi-Fi or no Wi-Fi, but you can allow colleagues, cabin crew to collaborate, share passenger information, share requests, do instant messaging without any Wi-Fi or internet requirement. And the other one, which there are others kind of where you have limited Wi-Fi in factory floor or elsewhere. But the other one that I think is actually really cool and more meaningful is about kind of sharing real-time location data in like disaster scenarios where you may have emergency services or members of the military who want to communicate where am I, what's happening, what hazards are around, and be able to share that without any infrastructure or potentially 4 or 5G connectivity in a forest fire scenario. So that's me, done. Final, put it together. What can you build with CRDTs, or what have we built at Ditto? An SDK that gives you a database API with heterogeneous multi-protocol replication across devices. They can sync without internet. You can keep accessing that data locally and reading and writing to it when they're disconnected, as is common with the kind of local first paradigm. And then when things reconnect, you've got the CRDTs to kind of beautifully handle the merging of changes that were made by concurrent collaborators. And for those of you interested in more the kind of overall architecture pattern, that would look something like this, with the local devices forming their own meshes, one or more of them replicating to an actual backend, which has to be in the picture somewhere, and then using something like an event-driven pattern to take those changes into your existing systems, or back and forth. So you're getting kind of edge-to-cloud connectivity as well as that local first pattern. So, sorry, I'm a bit over time. I hope that was interesting, useful. Happy to answer questions, but I assume probably save those until networking afterwards. How would you like to do it? Okay, yes, so thank you. Any questions now?
I have one question. So I've done some stuff a long time ago with CouchDB, and one of the thing that's interesting to me about this is obviously with the CRDT, that I guess the concern is there is this basic idea when you're working with something like Couch that you just accept eventual consistency. But this seems like that would be quite extreme. Like in many ways, especially if you were dealing with very, very disconnected clients, that you could have groups of clients that are all happily synchronizing with each other, and then one of them finally gets a net connection and that data goes up, and then like the data you have on the server could be kind of all over the place. How do you deal with that?
Yeah, I'm not entirely sure how to synthesize that question for the recording, but really this is one of kind of, I think, a perennial, like, you're accepting eventual consistency. And you may have, in my previous slide, a group of, this group of devices may have no connection. They all agree on one state of the world and they go along and they kind of merrily coordinate. And this other one over here is in the same scenario. And then, a week later, they both come online, they've substantially diverged, and do you want to kind of lose data? I think, honestly, part of it is an acceptance of the pattern. Part of it is also a data modeling exercise. So trying to avoid actually having conflicts in your data types where you will trigger a last right wins, scenario. So you could, lose data is another one. So you can, I kind of hate to push to like, oh, well, you need to model your data properly, but use, depending on what the use case is, creating, records that are, written in one place will subsequently be replicated. But if you had a requirement that this might happen frequently, you want basically both sides to arrive and maybe not just entirely trust the CRDT. So you have two separate documents in the end that you maybe go and say, I want to, resolve a more complex conflict.
It's almost like a user experience problem, as in, if you have that situation, the important issue is to present something to the user and saying, hey, while you were gone, all of these things happened.
Yeah.
What do you want?
Yeah, so then you pass it over to a human to do the conflict resolution. I think that's fair. I would say, though, that if you design well up front, which is not always possible, you can avoid most of those sort of unpleasant scenarios where you truly feel there is an unresolvable conflict. I don't think it's possible to eliminate them, and I would also say that, like, the co-founder of Ditto is at the back of the room today, who wrote a lot of this and could answer that better than me. So I'm sure he's going to shred me shortly. But yeah, I think you can avoid it in 95% of cases. And so, I do also believe that like there are some scenarios where you just can't accept that there could be a last right wins and you want to keep the entire history. CRDTs do sort of keep optionally a bunch of that history, but you need to work out what's my overhead for being able to sort of project to any state in the history chain.
Thank you.
Good questions. Any more? Yes.
Might be a really easy one actually. So I saw sort of the way your SDK works. You've got kind of a big Rust core. I didn't know that was a thing that you were able to get onto iOS devices essentially. And so I was just going to ask, did you have to do anything particularly special to run a bunch of Rust code on iOS, or is that just built in?
I may have to defer that question elsewhere. It's slightly below my level of expertise. But can we follow up like after the other talks, and we'll get the right, yeah, with a beer, that's fine. And we can also share it with the rest of the group, like by way of follow up if it makes sense. Yeah, sorry to dodge that one, but yeah, fair point. Yes, one more.
I saw that with the multi forms of connectivity, particularly with peer-to-peer, does then security come into a significant issue because you then have an exponent of both a third party who could disrupt, intercept, or cause changes which will destroy other places? Is that something you have to take into account, or is that something you just accept as part of the process? Or?
Yeah, so the question for others who maybe didn't hear him for the recording was about the security model in terms of if you have kind of this multi-protocol replication could be intercepted, is it safe? Could someone like inject a record that blew away state, projecting like a bit further out from your question if I understand it. So yeah, absolutely, like you need encryption between every peer. You need to manage like certificates and authentication, authorization between the peers. So like in our implementation, it's TLS 1.3 mutual auth between every single peer. You won't, if you're not authorized to connect, even if you had the keys, you can set kind of permissions per peer based on like the identity of that peer. That kind of requires you to at some point authenticate and authorize with the back end. But it's entirely valid concerns. I think you should kind of reduce it perhaps down to if you're using an unencrypted connection to anything, what would you do to that data in transit and at rest on either end? And you've really just got kind of an end-to-end version of that, which are solved and problems in general in terms of encryption and authorization. Great question. Yes, let's leave it there. Thank you so much, everyone.